He knows, he's on it.
Hi, I'm Peter Harrison from Southern Cross University, and together with Chris Doropoulos from CSIRO, we co-lead the Moving Corals RRAP project. And today, what we want to do is highlight some of the key outcomes from this work on the Great Barrier Reef over the last few years, which focuses on larger scale reef-based slick collection, mass culturing and deployment of larvae from wild coral spawn slicks for reef restoration. We also would like to begin by acknowledging the traditional owners of the land we're meeting on today and pay our respects to the elders past, present and emerging. And of course, we extend that through to all the traditional owner groups along the Great Barrier Reef on whose sea country we work.
So why larval seeding? Some work we conducted a few years ago, we highlight how propagals are incredibly effective at large-scale seeding in other systems. That includes some of the largest seeding programs in the world, using mangroves and seagrasses as well. So these programs have both persisted for many years and over very ecologically relevant scales. But how about corals? So we do know from small-scale trials that Peter and Dexter, dela Cruz and colleagues have done in the Philippines that corals can be restored to breeding populations on reefs within about 2 to 3 years in the Philippines. And some other work that Peter's led on the southern Great Barrier Reef has shown also to 5 years of breeding populations down there. But what's kind of limiting us is this scale. So these works have been relatively small in the scheme of something like the Great Barrier Reef. Some more recent work is showing getting a little bit bigger than half-hectare scales. So the question that we're kind of addressing in the Moving Corals program over these first 3 years is all about, well, how do we scale up larval-based coral reef restoration for effective long-term ecological benefit?
So the aims of the Moving Corals program is to develop this larger scale production of tens to hundreds of millions and eventually potentially billions of coral larvae with strong environmental tolerance that are derived from the collection of wild coral spawn slicks, which are reared directly on reefs and transferred for settlement onto damaged areas of the reef. So how do we go about doing this? Well, essentially we follow the natural coral reproduction life cycle. And the reef restoration, the larval-based restoration, consists of 5 research phases. The first phase is that we need to locate diverse breeding corals. And after mass bleaching events, the ones that are still surviving have increased heat tolerance. So this becomes our source reef for the coral spawn collection. We then undertake spawn collection in various ways and transfer the spawn across to reef larval pools or onto very large vessels, components and tanks. After the larvae are fully developed and desperate to settle, so they are fully competent, we release the larvae onto the reef directly, or we settle them onto devices or tiles, etc., before deploying them onto the reef, and that's the 4th phase. And then, of course, to find out what the outcomes of this process are, we need to undertake some longer-term monitoring. So just to highlight those phases in a little bit more detail, phase 1, we identify the source reefs with healthy breeding corals, and we undertake rapid gravid coral checks to confirm that sufficient corals are present with coloured eggs and are mature. We use the predictions of the major spawning nights to predict when we should be out on the reef to collect the spawn. And more recently, we've been working with the CSIRO modelling team to come up with hydrodynamic models which allow us to accurately predict where the spawn slicks will accumulate around reef systems. And for example, last year when we were working at Lizard Island, the hydrodynamic model predictions, as you can see there in the image where the hotspots are shown in red in terms of the likely accumulation of particles in a slick, matched almost exactly where we found the slick around those complex reef systems. The second phase consists of capturing the coral spawn. So predictable coral spawning allows us to access tens to hundreds of millions of spawned eggs. And so in 2022, for example, at Lizard Island, it was a split spawning period, so relatively few of the corals present were gravid, but we still managed to collect more than 30 million eggs very efficiently, which shows that this process can operate effectively even in light spawning conditions. Last year, we had a typical mass spawning with extensive coral spawn slicks, and were able to rapidly collect more than 350 million eggs in these mass spawning events, using simple collections in spawn nets and buckets.
Another process that we've been looking at in the program is scaling, other kinds of scaling techniques. So rather than more boats out on the water, maybe bigger boats with less people. And this kind of spun out from some earlier work that we did with oil booms, which they worked pretty well, but they're extremely difficult to operate with out on the water once you capture a slick and you need to maybe move it. I won't give you the whole history of it in essence of time, but we started working with a kind of a modification of a Newton net with bags that would roll out. After a couple of years of trialling that, we figured out that didn't work well. So one of my colleagues, Carlin, kind of came up with this idea, which is to put a kind of big scoop on a small barge, and we can get some rainwater tanks on that and pump the slick from the surface of the water directly into those rainwater tanks. And we know that those diaphragm pumps are really gentle on developing embryos. But in 2022, the operations worked really well, but our actual collection was about 500,000 larvae across a few nights. So it wasn't really good considering how much we can collect in a one scoop on a good night. But I let him try again. And last year in 2023, when we had a really thick slick, he made some modifications and got that kind of scoop net rather than attached to the vessel. It's floating on the surface, so we could skim right on the surface rather than a lot of the water column. So it helps concentrate that. And he came back after 20 minutes to the mothership and had kind of those 2 rainwater tanks full of about 30 million eggs. So a few years of persistence and failure, but with modifications, kind of helped us get there.
So we're now routinely culturing tens to hundreds of millions of multi-species competent larvae directly on the reefs, in the larval pools and on vessel tanks. And we know that we can scale this through increasing the numbers and sizes of these modular units. We're getting up to 50 to 60% culture efficiency out of these processes, and therefore we can start to optimise the way in which we deploy the numbers of these production units on the reef in future. And there are different scales of the pool net systems which have different capacities for rearing X number of millions of larvae on the reef directly. The fourth phase is about settlement and deployment of the larvae. So after 4 to 6 days, typically we've got a whole lot of desperate larvae waiting for the chance to settle on a reef. And so we can settle those onto hundreds or thousands of devices, similarly to what Carly was talking about in her talk. So we settle them onto devices or tiles before transferring them to the reef. And in 2022, we were working collaboratively with the CAD team at AIMS, CSIM, and we mass settled onto more than 1,000 of those devices. And last year, we did some mass settlement on more than 1,400 of the limestone tiles, and we have an estimated settlement rate for about 1/3 settlers on those. So we know that this process can be scalable.
So moving on to direct release of larvae onto reefs, which is where we think a lot of the scaling potential exists. We've kind of been working to this conceptual model since about 2018, where we use high resolution hydrodynamic modelling to look for high retention areas, and then using different kind of delivery approaches, we can try and pinpoint those areas to try and get larvae en masse onto the reef at large scales, but so they don't just disperse off from our kind of target areas. maybe it sounds simple, but this is probably our biggest challenge that we've been working a lot towards over the last few years. So one of the first things that we start to think about is, well, how can we actually identify that the larvae we release are our larvae? And so we came up with an idea of maybe tagging those coral larvae and digging through the literature. Dying larvae kind of, was a potential thing that we thought might be viable. So we ran some early tests on that in 2019, little pilot experiment. It was quite promising. And then we followed up with some experiments to refine the procedure. And it's really effective. And now we've field validated that. And now we routinely use it for many of our trials. That's published, and the procedure is really easy. Anyone can kind of do it. So basically, a quick journey is in 2021, we started to use these high-resolution models. We did a release from the surface, a cloud relief. We did get a signal in our cloud area versus our controlled, but it wasn't really ecologically relevant, nor after about a year once we were monitoring our permanent plots there. 2022, we then used a lot of instrumentation to try and look for these really low current periods, and we also did quite a controlled manipulative experiment on the reef to look for how effective it can be if we really hit those target slack current periods. Oh, it's not working. We also kind of altered the way that we do our delivery. Rather than a stationary point source, we did kind of curtain approach of release, and we started using rhodamine to visualize the plume. And we effectively kind of covered a broad area of these patch reefs, a bit over a hectare, and we got a bit of a signal. We found our blue larvae, but it wasn't super ecologically relevant yet. A few months ago, we were releasing from the larval pools near these patch reefs and directly from a vessel as well as having, the CADs and the tiles in the other culture pools. We've got different sensors on the reef and in the air and etc. We've got different really high resolution unstructured modelling going. We really understand the tides very well as well, so it's really important to know what's happening with currents in the area. And we get these really 12-hour periods of less than 0.02 metres per second tide. It's very slack. We've got things in the air looking at rhodamine and sensors. We're getting really high retention, so it's matching the modelling and the instruments. And you can see that we actually this year got a 2 to 3.5 times signal from our free releases of instantaneous settlement. So this is 2 days after our release compared to our control plot. What you might see on the far right is that compared to when we constrain the larvae under these big nets, there's 60 per tile. So that's an order of a magnitude higher. So we're getting more than our no larval release control, but compared to constraining it, where it's almost insignificant. However, the team just got back, a few weeks ago, and you can see after 3 months, actually, those sort of densities at that size actually become meaningless because you get extremely high mortality. So, we're going to now move on to monitoring those corals on the benthos, so that's on the reef, using this micro-imaging technique that Marin Gouezo developed and published. It's fully accessible as well, open access. And so we're going to monitor those over these, coming year to start seeing whether, we have effect sizes of the juveniles on those plots, because that's what matters, not what's happening on a tile, but what's happening on the reef.
Okay. So, yeah, we are now looking at various trade-offs between mass deployment of pre-settled larvae on tiles versus the free releases and working out how to optimise those. So in conclusion, many of the reef trials show larval restoration enhances settlement and recruitment, even on highly degraded reefs. Pilot-scale developments for the future will be focusing on upscaling the production of hundreds of millions of larvae from genetically diverse spawn slicks, mass settlement on devices, and optimised larval release for multi-hectare restoration. And the plan is to overcome the inevitable juvenile coral loss through increasing larval production and settlement, feeding the larvae to increase energy supplies, co-culturing with symbionts, and selective breeding for increased enduring success. What we do know is that enhancing larval supply and recruitment is essential to restore foundation corals and genetically diverse breeding populations. Thank you.
Now, does anyone have any questions? This is an absolute incredible undertaking, gentlemen. Really innovative and impressive.
Thank you. So a question from the Slido: how long do the larvae stay died, i.e. how long can you monitor their survivorship compared to natural larvae?
So in a larval form, at least for a week, but then after that we kind of settle them. But following metamorphosis on the reef, in a lab at least 10 days, but from when we revisited things on the reef, less than 2 months. So yeah, it's not a long-term stain, it's just for a short-term signal.
So I actually just kind of want to add to that. With the dyes that you're using, are they fluorescence-based? And with your microimaging techniques, would you be better off potentially using a fluorescence one and seeing if you can get a stronger signal that way and track them maybe even potentially longer?
Yes, I think the Nile blue does have a light spectra. As with the neutral red, we tend to use the Nile blue because it doesn't have any toxicity. With a neutral red, you have to be really careful with it. So there are light spectra that you could use. You would just have to be careful once the zooxanthellae enter, because then they're going to start setting off different light spectra as well. We haven't applied that, but I'd love for somebody else to give that a go, and it should work too. But yeah, you would need different equipment, so yeah. We try to make it very basic. I'm simple.
Any more questions? We have time for one. So another question from the Slido. Since RRAP moving corals trials began, you have 2 years of tracking survivorship and seeding recruits around lizard. What is 12-month plus survivorship of these efforts?
So it varies significantly depending upon how many larvae were deployed, how they were deployed, and the reef environment themselves. And in addition, where we've done trials on the cats. So what we do know is that when you settle larvae onto devices before you deploy them on the reef, that the initial settlement rates are much, much higher, and therefore the numbers of recruits produced are higher than that. But for the other components of it, as Carly mentioned in her talk as well, there is great variability depending upon the substrate, the amount of CCA, and the amount of competitive algae in the system.